If we take the equations we computed in the previous video on the Euclidean algorithm, and I've listed them here. So when we ran the Euclidean algorithm with 1071 and 462, we got these three equations. We can rewrite both the second and the first equation by solving for the remainder. So we solve for the remainder in all of our equations that have a non-zero remainder, and we get these guys. Now, there's a 147, this sort of intermediate remainder that we found, in both of these equations. So what we can do is we can plug in that 147 into this spot. And when we do that, what we find is by plugging it in, we get 21 is equal to, that 21, when we write equal to like this, 21 still stays on all those sides, on the left-hand side. 462 minus 3 times, substitute that in. So we multiply our -3 to the first one, and our -3 times -2 is a +6. Okay, great. Now there's one 462 here, and there's 6 here, so that's 7 462s. So this is interesting. So 21 was the GCD of 462 and 1071. And we actually found integers 7 and -3, so that, well, when we multiply that integer, let's say x is 7 and y is -3, so x times 462 plus y times 1071, we actually get the GCD. We get 21 when we use those. And these numbers are special to this situation, but in general, you can always do this. You can always solve this equation where 462 is A, 1071 is B, and on the right-hand side, you have GCD of A and B. And they're called Bezout coefficients or Bezout coefficients. So in general, there's this theorem which says that provided A and B are not both 0, if they're both 0, you can't make sense of the GCD. But if they're not both 0, then there exists integers x and y such that the GCD is an integer linear combination of A and B. That is, I multiply A with a certain integer and B with a certain integer, and I get the GCD of A and B. Now, furthermore, the GCD of A and B is the smallest positive integer that you can actually write of that form. You can't get away with any smaller. So not only can you do this, but the GCD of A and B is sort of the best case outcome. You can't do any better than that.